Hello everyone, my name is Namho, and today I'll be presenting my implementation for assignment 2, uh, gradient domain processing and Poisson blending. So this assignment focuses on gradient domain image processing with a particular emphasis on Poisson blending and its wide variety of applications. So if we just, as we discussed in class and elaborate in this report, the core insight behind gradient domain processing is that human visual perception is more sensitive to relative changes in intensity, so that is gradients rather than absolute pixel values. So by manipulating gradients and then reconstructing images from these modified gradients, we can achieve effects that would be impossible or very difficult with traditional pixel-based methods. So today I'll walk you through my implementation following the structure of my written report. First, we'll discuss the toy problem that verifies as a framework. Second, the Poisson blending for seamless image compositing. Third will be mixed gradient blending for texture preservation. And fourth, three custom examples showing real-world applications. And lastly, the bonus implementation of gradient domain like color to grayscale conversion, which was inspired by the Gradient Shop paper. So let's begin. So uh, in the first task is what we call the toy problem. So this here, we are tasked to reconstruct an image from its own gradients. So this originally might seem simple or very trivial since we already have the image, but it serves as an important purpose because it verifies that our gradient domain framework is working correctly before we move on to like more complex tasks later on. So here's how it works. So given an image, we first compute the horizontal and vertical gradients at every pixel location. So a horizontal gradient tells us how much the intensity changes as we move from one pixel to the next in the x direction. And similarly, a vertical gradient captures the changes in the y direction. So the reconstruction is formulated as a least squares optimization problem. So for an image with height h and width w, we create the h times w variables representing the unknown pixel intensities that we want to solve for. So then we reconstruct a system of linear equations from horizontal gradients, and each equation takes a form of like v at position x plus 1, uh, minus v at position x, y equals to the source gradient at the location. And similarly, for vertical gradients, we have v at x and y plus 1 minus v at xy, which equals to the vertical gradient. So the gradients alone only tells us about relative intensities, not the absolute values. And so to fix the absolute intensity levels, we add another anchor constraint. So we simply say that the reconstructed pixel at the top left corner must equal to the original value at that location. So uh, we can the complete system can be written as a minimize the square norm of AV minus B, as you can see here, uh, is so where A uh, is our sparse matrix encoding of all these gradient relationships, and V contains all the unknown pixel intensities, and B contains the target gradient values. So in the implementation, as you can see in the toy reconstruction.py, we use a sparse matrix for efficiency. So for our test image, which is 119 by 110 pixels. So this is a very large system if we compute the number of variables and equations, but a sparse matrix technique makes this more efficient to solve. So let me walk you through the key implementation steps. First, on line 44, we create an image to variable mapping that converts the 2D pixel coordinates into variable indices. And then for each color changes, starting at line 60, um, we um, we build a sparse linear system. And then if we move to line 69, as you can see here, through 83, so this chunk. Um, so here for each pair of horizontal adjacent pixels, we set the coefficient to 1 for the right pixel and coefficient -1 for the left pixel. And the target value is the actual gradient from the source image. And if we move from line 85 to 99, the vertical gradient constraints is done in a similar manner. And then finally, about around 101 to 106, we add our crucial anchor constraint. So we're setting, as we said before, the top left pixel to the original value to fix the absolute intensity level. And to do so, we use the SciPy ls square, so L square solver here, which the reason why we do this is so that we can efficiently handle the overdetermined sparse system. So each color channel is processed independently using the same framework. So if we look at the output, uh, here are the results. On the left, you see the original image, and on the right, you see the reconstructed image from the gradient only, plus the one anchor pixel. So I can see the reconstruction is actually nearly perfect. So the mean square error is only 0.00354, but I rounded up here, which is extremely small. So this tiny error comes from the floating point precision and the least square approximation. So visually, the two images are essentially identical. So this confirms that our gradient domain framework is working correctly, and we can successfully compute gradients to build a sparse linear system and also reconstruct the image. And thus, this gives us confidence to move forward to the next task. So now we move on to the main task, which is Poisson blending. And the goal here is to seamlessly merge a source image into a target image. So unlike simple copy and paste, um, which creates the visible seams due to the lighting or color differences as we discussed in class, Poisson blending is a more advanced technique that adapts the pixel values to fit naturally while preserving the source's internal structure. So mathematically, Poisson blending works by preserving gradients from the source while matching the target at boundaries. So we have two types of constraints. The first one is for the interior pixels. So where both pixel A, for both a pixel I and its neighbor J are inside the source region. And so we enforce gradient preservation. So the equation is Vi minus Vj, which equals to Si minus Sj. Um, so the significance is that this ensures the internal details and textures of the source objects are maintained. Now the second is the boundary pixels, where pixel I is inside the source region, but the neighbor J is outside. We use the target image's boundary values, so the equation is Vi equals Tj plus the source gradient Si minus Sj. So in other words, this can be understood as we take the target's boundary value as a base, and then we add the source gradient. So the resulting effect is that ensures smooth transitions of the edges. Now, if we look at the code implementation at the Poisson blend, uh, here we use a bounding box optimization to reduce computational costs. So if you look at line 59 all the way to 73, um, you can find the minimal bounding box containing the max and add one pixel of padding. So instead of creating variables for all the pixels in the entire image, we only solve within this box. And this is necessary because it improves efficiency for small objects in the image. Now, if we move to line 88 here, we create the variable mapping for the box region throughout 101, where each pixel gets a unique variable index. And now the core algorithm actually starts in 116 here. So we use for connectivity, which is defined in line 113 here. So this means that as for four directions, up, down, left, and right, and for each mask pixel, we check for all the neighbors. So just to go into the key logic with the mathematical implementation here, from lines 146 to 155, we add a boundary constraint using the target value, so Vi equals Tj plus the source gradient. So this ensures a seamless transition of edges. And then at line 164, through 166. This solves the system of least square at lines 169 to 174. We insert the solution back to the full image. So if you can see here, when we do so, each color channel is processed independently starting at line 104. If you go back right here. So yeah, let's jump into the results. Here, the results with the provided image of the penguin images. So replacing the penguin onto the snowy hiking scene. And so we can look at how seamlessly the output is integrated. So the penguin is integrated. Just zoom in a bit more for the sake here. And so there's no visible seams at the edges, as you can see, and the boundary blends smoothly into the snow. And you can also notice how the penguin's over brightness has sort of adapted to the surrounding areas to match the bright snowy environment. So this color adaptation actually happens automatically because we're preserving the gradients, but allowing the overall intensity to adjust based on the boundary conditions. So all in all, the technique works particularly well here because the penguins have like strong internal edges. Like if you look at the beaks, the eyes, and like the body outline, which are preserved through the gradient constraints, so while the overall lighting harmonizes the scene. Now, um, we can move on to the mixed gradient blending. So, 1 second. Yeah. So in the next part, I'll be discussing what mixed gradient blending is. So this part actually extends Poisson blending with a slight important modification. So if when we looked at before with Poisson blending, it always uses gradients from the source image, right? But mixed gradient blending actually adaptively selects gradients from both the source and the target magnitude. So the motivation is simple. So this is like sort of a comparison where Poisson blending can sometimes over-smooth or lose important textures from the target image. So for example, if we're blending onto like a highly like textured background, like water or grass, we might want to preserve some of the textures with the blended regions. So this work is actually implemented in mixblend.py. So the structure itself is very similar to Poisson blending, but as I said, one crucial difference with the gradient selection. So for each pixel pair in each direction, we compute both the source gradient and the target gradients. So if you look at line 110 through 118, right here, uh, so this is the heart of the algorithm. So line 111, as you can see, to 118. Sorry, 111, it computes the source gradients, like source channel, as you can see here, and then we compute the target gradients here. And then from 115 to 118, we actually perform the selection. So if the absolute value of the source gradient is larger, we use the Dij to source gradient, but otherwise we use the target gradient here. So the selected gradient d of ij is then used in our reconstruction constraint. So line 120 to 130 handles the interior pixels, so both pixels in the mask, where we enforce vi minus vj equals to dij. And uh, lines 131 to 139, as you can see here, um, handles the boundary pixels, where we use vi equals tj plus dij. So this like per pixel per direction decision generally allows us for strong features from both images to be preserved where the source has strong edges. So like if you look at the penguin's beak, so yeah, for this image, like if you look at the penguin's beak is very well preserved, um, where the source has strong edges like the penguin's beak, where the target has strong textures and the source is like relatively like, smooth, the target texture shows through, as you can see here. Um, yeah, if like just to, sorry, so, yeah. So for the sort of like comparisons, as I said, I just wanted to highlight some of the key differences. For gradient selection, Poisson blending, it always uses the source gradients, whereas the mix uses the gradients from the larger like magnitude. Texture preservation, well, Poisson blending, it replaces target textures completely, whereas the mixed can preserve textures from both images. And in the best use case, Poisson works best with distinctive objects, so with like simpler backgrounds, whereas the mixed is better for textured backgrounds or semi-transparent effects. And in terms of computational cost, Poisson blending is pretty standard, uh, but mixed is slightly higher because of the gradient comparison step. Now let's just discuss some of the results here. So here, the mixed results, mixed gradients with the same penguin images, whereas, yeah, the source is a bit different. At first it looks very similar to the Poisson result, as you can see here. Let's just zoom in a bit to see the output. Um, as you can see here, right, the penguin is right there. But if you look closely at the regions where the snow has strong textures, in those areas, some of the background texture is subtly preserved in the blended region. And you know, as I said, the penguin has like really strong features like the beak, the eye, and like uh, has the body outline. So this is also somewhat preserved. So- if you look here, uh, yeah, it's typically stronger than the backgrounds, but in smoother regions, the penguin, where the source gradients are weak, the snow texture can be shown through like slightly, as you can see here. So this demonstrates how like mixed gradient provides more control over texture preservation while sort of maintaining the boundaries seamlessly. Okay, sorry. Yeah. So now let's look at the um, three custom examples for the three custom examples that I created on these test methods in the different scenarios. So for each, we present like sort of a unique challenge that helps us understand when each method works best. So if we look at the source images, so I had like a fruit bowl, um, the Keist keychain, a house, the moon, the ocean, and a shark here. Yeah, and so uh, starting with the example one, which is like shark on the moon. Uh, what I wanted to do was sort of blend a shark onto the moon's surface, and this tests how like the method handles like different like very extreme lighting differences. So the shark is relatively dark, whereas the moon surface is very bright. So using the shark JPEG and the moon JPEG, sorry, the shark as the source and the moon as the target, but we both resized the image to 50% for computational efficiency and hand drew a polygon mask around the shark using the get mask .py function that I had here. Yep. So if you run this, it allows you to actually run the manual like mask around utility function, and then we place it into the center of the moon surface. So here's like a simple paste on the left, as you can see here, and you can see the harsh edges around, very unnatural. In the middle, you have the Poisson blending, which successfully integrates the shark into the lunar landscape. But you can notice how the shark appears significantly lighter than the original form, so the color is like red. And this is how the color adaptation works, and the boundaries are completely seamless, despite the like drastic like lighting differences. And this sort of demonstrates like Possum Blending's ability to handle like different light variations while maintaining the shark's internal structure. Now on the right, you have the mixed gradient version, which shows a slightly different texture characteristics. So some of the moon surface textures bleed into the smoother regions of the shark, sort of creating slightly more integrated appearances. So both methods sort of handle this challenging scenario with each like aesthetic, right? Now the second example is the um, the implementation can be found in uh, uh, sorry in the custom script, as you can see on the screen. But if we look at example two, which is the Keist mascot on fruit, um, you know, this is sort of an unusual combination that tests both the like architectural blending textures onto the like an organic surface with red color texture. So, for example, I use the Keist JPEG, which shows the Keist mascot, and the fruit JPEG, which just has some colorful fruits. And again, we resized to 50%. And I created a polygon mask around the main mascot structure and placed it over the fruits, as you can see. Now, if you look at the simple cut and paste, although the mascot like stands on top of the image, and as I said, the edges are very harsh and there's a clear mismatch in lighting. The Possum blending in the middle sort of preserves the geometry of the mascot and adapts to the structural patterns and overall color tone, which sort of harmonizes with the fruits in the background. But you can notice how the mascot takes on much a warmer and brighter color, so very vibrant to match like the fruits in the background. And this sort of harmonization happens automatically through the boundary constraints that we discussed before. Lastly, the mixed gradient version on the right shows a more fruit texture showing through the mascot. So in particular in regions where the mascot has like relatively like uniform areas and the fruit has like very strong texture gradients, the mascot like the strong edges, like you can see the geometrical patterns remain well defined in both methods. sort of demonstrating how it's sort of well preserved, albeit this is more see-through than the Poisson blending. Now, lastly, I would like to discuss the house on ocean, which is a bit more challenging, I think. So for this example, I'm using the house JPEG as well as the ocean JPEG. So house being um, containing like different architectural details, and the ocean having like somewhat complex wave patterns. And as I said, like all the other examples, we resize to 50%, and I create a polygon mask around the house structure and place directly on the ocean surface. So this example is actually one of my favorites. It sort of it particularly highlights the differences in the two methods clearly because if you look at the Poisson blending, well, the simple paste was very challenging. As you can see, there's clear like additional artifacts created. But for the Possum method, like the result, the house is sort of cleanly integrated, but with its initial textures completely replaced by the gradient-driven reconstruction. And the house sort of adapts to the blue tones of the ocean, and it appears somewhat naturally lit for the ocean environment. So you get this very clean and well-defined house that looks like it belongs like sort of like in the scene. But if you look at the mixed gradient results on the right, it tells somewhat of a different story because it allows for more of like the more accepts more of the ocean wave patterns to appear within the house. So this creates some of like a very interesting semi-transparent or like ghost-like effect. So the house, like strong edges, like if you look at the roof lines, the corners, the different features, they still remain visible because the gradients are stronger than the oceans, but the interior sort of picks up on the oceans like flowing patterns, where the house has like weaker gradients. And this could be seen as a failure if you do want like this solid opaque house. But I guess in terms of like artistic effect is your goal, then this is successful. So I guess it demonstrates like this trade-off between like the texture preservation as well as the main object like solidity. Yeah. So yeah. So just to summarize, all the implementation so far, the Possum blending implementation can be found in the Possum blend.py script. And so it consistently produces seamless integrations with no visible like boundaries. But there are some cases where we see more dramatical effects occurring. Now the mixed blending script is here. In this case, it provides some of like a middle ground whilst it maintains like seamless edges while allowing like the target textures to show through in the low contrast source regions. Um, there are some instances where it sort of, uh, you know, prioritizes like this artistical value of the image. So, um, a common observation, I guess, across all the methods is that both work best like when the source object has strong edges and the target has relatively smooth regions or near the boundary. And the performance definitely degrades when both source and target have like complex high frequency textures and at boundaries, and the gradient constraints can conflict to produce these different artifacts. And so the two methods at least handle like extreme lighting differences well, but at the cost of like different color shifts, as you can see here. And as I noted in my report, these failure modes and success cases can help like sort of build a good intuition of to apply these techniques in practice. And lastly, for the bonus section, where we implement the gradient domain processing, so the color to grayscale conversion. So this addresses the specific problem with like standard grayscale conversion methods. So when we discuss like the standard grayscale conversion, it basically computes the weighted average of RGB channels, approximately 0.2299 for red, 0.587 for green, and 0.114 for blue. And these weights are basically based on the human luminous perception and work well for most images. However, they are shown to like fail catastrophically when colors have similar luminance but different chrominance. And the classic example is sort of like um, the Ishihara colorblind test. So in the color version, you can clearly see the number 35, but by like red and green dots on the gray background. But if we apply like standard like, gray conversion, the number becomes sort of like invisible, and the red, green, and gray regions are like all have the similar luminous values, so they map to similar gray values, and the color is like distinctly lost, right? So if we look at the script of color to gray dot pi here, and the main algorithm, so the key insight is that the color differences create gradients in individual color channels, even when combined luminance is weak. So if we start with like line 47 here, we get the standard grayscale conversion using the scikit images like RGB to gray function, which serves as our baseline initialization. And then in line 49 through 58, we handle the color space selection. So if you use the use RGB gradients as true, the Boolean value, we work directly with RGB channels. So if it's false, we convert to the HSV with RGB to HSV function and work with hue, saturation, and value channels. And third, if we move to line 60 to 74, we compute the gradients for each channel, and for horizontal gradients in line 68, as you can see here, we compute the difference between adjacent pixels in the x direction. For vertical gradients in line 73, and compute the difference in the y direction. So the next step being fourth, this is the unique contribution that I tried is in line 76. So to 90, we perform like a maximum gradient selection. So for each pixel location in each direction, we compute the absolute value of gradients across all three color channels. And then line 83 to 85, we select the X gradient with the maximum magnitude. And line 88 to 90, we select the Y gradient with maximum magnitude. So this identifies where the most significant perceptual differences occurs, and like regardless of which color channel it comes from. And lastly, if we look at line 96 to 142, all the way down, um, we reconstruct the grayscale image from the selected gradients using the same least square framework that we used earlier. However, I think the most crucial part is that if you look at line 135 through 142, we actually add a soft constraint to stay close to the grayscale value. So the reason why we do this is so that it prevents the solution from sort of drifting too far from the automatic regularization. Yeah. So if we look back at the report, the optimization objective, it balances two terms. So minimize is the alpha squared times the sum of vi minus vj minus dij squared plus the sum of vi minus gi squared. So here dj, it represents the selected strongest gradient between the I and j, pixels I and j, and gi represents the standard grayscale value at pixel I. So the first term um, weighted by the alpha squared enforces the selected gradient. So you can see that the implementation is line, where is it? Sorry, 111 to 133 of the script, where we add both the x gradient and y gradient constraints, each weighted by the alpha value. And the second term, it actually keeps the results close to the standard grayscale values at each pixel. And this is implemented through line 135 and 142, right here, where for each pixel we add a constraint that vi should equal the standard grayscale value gi. And the parameters that I used, parameter alpha controls the balance. So higher alpha means like 2.0 means stronger gradient preservation and more visible distinctions, and lower alpha like 0.5, it means you're staying closer to the standard grayscale with subtler effects. And sort of in my experiments, I use alpha that equals to 1.0, which I sort of found that it provides a good balance between preserving chromatic gradients and maintaining reasonable overall appearances. And as instructed from the assignment, this implementation was inspired by the gradient shop framework by Bate al. paper, which was referenced in my report. And I made several deliberate simplifications and modifications. So I discussed this in my report. Um, But the core idea is that the idea of operating on gradients and reconstructing images through, optimization is directly inspired by their work. However, I made, I think, four key modifications. The first one being that is for edge detection. So instead of their the gradient shops, like they have a very sophisticated long edge detector that identifies continuous edges and ensures like spatial coherence. Uh, I I developed like a much simpler maximum gradient selection approach. So this method um, operates independently at each pixel location and by selecting the gradient with the largest magnitude from all color channels. So while this is slightly less sophisticated, it's much easier to understand and implement, and it still achieves the primary goal of preserving color distinctions. So the trade-off is that I may lose some spatial coherence, but my soft constraints provide a regularization that mitigates this issue. The second one is the constraints. Instead of hard anchor like pixels or boundary conditions, I use soft constraints that encourage the solution to stay sort of near the grayscale values. And this approach, implemented in line 135 to 132 in the code base, is more numerically stable and actually provides automatic regularization without requiring careful selection of anchor points. Now for the color space, um, I offer like RGB and HSV options instead of the lab color space like the paper actually likely uses. While lab is like perceptually uniform and theoretically better, I think RGB and HSV are more accessible and I believe to be more like easier to understand and still produces good results for this purpose. And lastly is the optimization. Um, you know, I use the direct sparse linear solve with the least square rather than the iterative methods that might be employed for like handling additional constraints or real-time processing. So these like simplifications maintain the essential like gradient domain processing like philosophy, I would say, while making the implementation much more accessible. So let's dive into the results. So if you look at the left of the uh, sorry, if you look at the colorblind test image on the left is the standard grayscale, as you can see right here. This is the gradient domain grayscale with RGB gradients, and then here is the HSV gradients. So in the center is our gradient domain grayscale using RGB gradients, and the number, I mean, it's still like the HSV, you can sort of still see the 5 here on the right. But the algorithm identifies the different chromatic gradients while preserving the reconstruction as best as it can. And so this is definitely a dramatic demonstration of gradient domain processing while preserving the sort of the perceptual information that would otherwise be lost. Now let's look into some of the natural images examples. So on natural images, the effect is more subtle, but still I would say beneficial. As I discussed in 5.6 in my report, for the fruit image, you can see the comparison between the standard grayscale, the gradient domain, as well as the RGB and the HSV. Standard already produces like actually reasonable results since the fruit has like it naturally has like varying brightness. Our gradient domain method produces slightly similar results, but slightly enhanced separations between the fruits. I know it's very subtle, but I think it's definitely visible. Um, and if you look at the HSV version, you can see like uh, the saturation differences are much more apparent in this example. So I think uh, yeah, so these are the differences. And then for the penguin image, which already has strong luminance contrast between the black and white plumage, the gradient domain method produces results very similar to the standard grayscale. And this is very expected because when an image already has good luminance variation, preserving chromatic gradients, it provides little to additional benefits. So, the soft constraints outlined in 135 to 142 uh, sort of ensures a method gracefully degrades to the standard grayscale in these cases. So it doesn't really make things worse, only better when chromatic information is needed. So this sort of demonstrates the robustness of our approach and it improves the results when needed. And like with the colorblind test, it tries to maintain the quality of the normal image where standard methods already work well. Yeah. Um, so yeah, so all the code can be found in the submission. And yeah, thank you so much for listening.